Thank you, Robert. That was great. I'm going to share my screen now. So tonight we're going to go through, let me know if this is, I'm going to increase the size a little bit of my screen, but can you guys get that better? How's that look? Perfect. Okay. So tonight we're going to go through one of the Kaggle courses. These are what they call their micro courses. Generally take maybe a day or two to finish these, maybe a little longer depending on your time, but they're very straightforward. And tonight's is on computer vision. And it's interesting, before I start, I wanted to point out that this is a very new one. I think they may have redone it. And it, as opposed to some of the ones we've seen in the past, this one seems to cover more of the theory than I normally see, which is, I think, a good thing. A lot of times they basically just do enough to get you started and refer you to some links to go through some of the theory. So we'll start off by looking at what is a convolution classifier. This has been a very standard way to do image classification, where you look at images. And so let's go ahead and jump into the theory part, or the tutorial part. Here in the computer vision, we're going to talk about building an image classifier, where we are presented with an image and we have the model determine what class the image is. In this case, they're going to use a data set that has cars and trucks, and we'll be deciding whether the image is that of a car or a truck. We're going to make our own deep neural network called a convolution net, or convnet for short. And it's going to have a bunch of different blocks that compose it, and we'll go through how that's done. We're going to learn some very fundamental ideas about feature extraction from an image. We'll go through that, and then we'll master transfer learning. There are many very powerful models out there that have been trained on gigantic sized data sets for a long time with a lot of compute power that you probably wouldn't be able to do on your desktop, or even maybe even your machines at work. But we can take advantage of that training to do our own predictions, and that's done through transfer learning. We may have seen that. I think we've seen transfer learning before, but this is with image models. So, and then the last section we'll go over is data augmentation, which helps when you have a small data set and you want to maybe have a larger data set to train on to increase the accuracy of your model on unseen data. So here in the introduction, as I mentioned, convolution neural networks are sometimes called convnets, or a lot of times they're called CNNs for short. And we're going to apply these to image classification. So given the picture, we're going to specify what that picture has in it, or what it is. You can do more with these type of networks that involve image segmentation, where you maybe put a mask over a certain object and detect where in the image that object or multiple objects are. So that's a further thing you can do. We won't do that here, but and then you can also go from this to do things like general adversarial networks for producing art, and many other types of use of those. But we won't go over that here. But once you understand what a CNN network is, you're set for learning those other uses. The basic idea of a convolution classifier model is we're going to take an image as input, and that's going to be, as you'll see, usually a set of pixels. It describes a digital image. And then we're going to have the base part of the model, which is going to extract out features. And when I say features, I mean things like maybe it has a feature that detects, does it have tires? Does it have windows? And you could have something that detects colors, and many different types of features. Some are low-level features like lines and circles, but you can then do higher level features that put the lines and circles together to detect more complex features. And then all of these have a head, which is usually a dense network. It doesn't have to be, but it's normally a dense network that allows you to then take those features that you've extracted from an image and identify, well, the ones that have these certain features are cars, or the ones that have these certain features are trucks in our case. Here, they're saying, you're going to output, this is a VW bug, as an example. So we're going to extract features. We're going to then go ahead and classify those and output our prediction. Here's just another example of how that feature extraction is happening. Maybe these are high-level features that come out. We're going to go through and produce a network that we have the goal when we train it to determine which features to extract from an image. And I'll go through this in the next lesson, but how we're going to choose which features. The network learns which features are the most valuable for doing the classification, and then which features those classes are attached to. It's a basic thing. I mentioned the idea of transfer learning, and the way that's done is we have those base part of the model that extracts the features. We can reuse that. Maybe it was trained on ImageNet, which is a huge set of data that includes not just cars, but boats and dogs and all kinds of plants and other things, right? But it was trained on a very, very large data set to identify kind of low-level features. We can adapt that model and add a new head or a new set of classes that do all the classification part of it based on those features, and adapt it for our particular use case. The first thing we're going to do is as I mentioned, is this car truck model. The data set has 10,000 pictures, which is a good amount of various automobiles, and it's pretty well balanced between the trucks and the cars. They're just showing here that they're going to load it into a data set for training and for validation. In this case, you can see it's actually a pretty even size between the validation and the training, and they both have the two classes. We're going to start off by doing a transfer learning with a model that was trained on ImageNet, which, if you're interested, you can go back and look at what that involves, but they're a very large set of images, millions and millions. And we're going to use a model called, go ahead.
David, before you go, do you mind expanding that code block? There's a few examples of images we can look at. I think it's always helpful. Yep.
Yeah, it doesn't
have any. Okay.
Yeah, it doesn't show them here. It shows them in the exercise. So we'll look.
Okay.
Yeah, it says they show them here, but they don't. So there's a couple of strange things in this exercise, but the model we're going to use is VGG16. It's a popular convolution net with 16 layers is really what the 16 stands for. So this model, they've already got it saved out, and we're going to load it into Keras as a model. And we're going to set the base layers here. They don't have the head attached to this, so they don't have the part that does the classification. They're just the part that does the feature extraction. We're going to set that as trainable as false. So we don't want to change what it's already learned. So we're going to start this way with it set as false. And on top of that pre-trained brace, we're going to add something that flattens out this convolution, output these features into a one-dimensional vector that goes into our dense layers. So a typical way that you want to get it into a form for your dense layers. We're going to apply a ReLU activation, which I'll go through in a minute. And since we're predicting whether it's a 0 or a 1, which stands for car or truck here, we only really need to know, is it a 0 or 1? So we only need one output. And the good activation for doing these type of binary classification, it's called, is a sigmoid. So we'll look at that. They're just showing an example of this, and we'll go through in detail all these steps later on. But here we're just going to do as I said, we're doing binary cross entropy with binary accuracy to measure how well our model does. We're going to fit it. This is very standard stuff we've seen before. And here we're going to do 30 epochs. We're just going to go through. And the one thing I wanted to look at maybe is the validation. Right here, validation loss gets to be 0.3085. So just try to remember that riddle if you can. But we can look at this graphically and see how our training went. You can see we didn't, although the model kept training and getting better on the training set, the validation set pretty much peaked right about here down near that 0.3085. The accuracy at that point on the validation was around 87%, if I recall. So pretty good result right out of the box with a very simple model, not doing anything complicated. One thing to notice is it rapidly starts to overfit the training data. So there are many different steps that we've seen before for handling this overfitting behavior, but we're not going to do anything complex yet. That'll be getting into later. So let's move on to the exercise and see what they have us do there. So one thing I want to point out that's really important with these type of image data, you can have a very large number of parameters or weights that you're training in your model. And sometimes your data sets can be very large and you want them to be quite large for it to be effective. So it can be a slow process on a CPU. And this is the case where these GPUs can do a lot of things in parallel and really, really help with the speed of the training by many folds. If you also do it with a TPU, which I think Neil is going to cover on Friday, you can get even better, faster training and results with TPUs. So I would turn on the GPUs when you're doing this type of work. One thing to notice here is they're doing a lot of, this is where they're loading in the data that we'll need and the libraries that we need for scoring in the exercise. They do, I've never seen them do this as much, but this is a great example of how to set all the random number generators to seed them so that you'll get consistent results. So they're looking at when they're examining how our solutions are here, they want to have a consistent result to compare with what they believe is the right answer. So somebody's getting their warning. So here's where they're loading the data sets, and I want you to just notice that these are TensorFlow data.dataset things where you can load an image data set now directly from the directory. I believe this is new in 2.4 version of TensorFlow, but it's a nice little utility to have. We're going to load in images that were sized as 128 by 128, so nice square images. And they're going to shuffle the input from the training. I'm not going to shuffle it when we do our validation because it doesn't help us to do that. The other thing to notice is that they're going to use this auto tune parameter to set the amount that we prefetch. That helps speed up. You can do a lot of these activities like prefetch can be done on the CPU while the GPU is training. So you don't get any lag with loading up data for the next training in the next batch. So this helps a lot with speeding your training. The other thing they're doing here, because this is a relatively small data set, the size of the images is pretty small, is you can cache this in memory, which really speeds up things. So you only have to go to disk one time. So I don't know if anybody noticed when they did the training here that the first epoch was really slow, and then after that it's very fast, and you'll see it here in a second.
Yeah.
So instead of using VGG16, we're going to use another pre-trained model, which is also trained on ImageNet, called Inception V1, and they've loaded up that base part of the model here for us. You can also get a lot of these models, pre-trained models, out on the TensorFlow hub, which has directions on how to load them there. So again, we're going to set that base model trainable to false. So we're not going to train or change the pre-trained weights that it has. We're just going to go with the features, how they're selected. They want us to attach a head where we flatten it out, and we have the 6 and then 1 for prediction of a car or truck. And it's very much similar to what we saw before. So we're doing that here. And then we're going to train this. And again, we're training looking for binary accuracy. The model is being trained here. I mentioned the first epoch is slow, almost a minute. And then after that, it's very fast. So even though we're going through the same batches with the same model layers and nothing's changed, this is going to be a lot quicker because those steps and parameters we set on our data sets to make them quick.
Can I ask a question?
Yes, please.
Yeah, this is actually the first time I have seen why the first training epoch is much slower than rest. Is there a specific reason?
Yeah, so the first time it comes in and starts to train, it goes to our data set object that they've set back here.
It's because of prefetch?
It has to load it the first time all the way into memory cache.
Okay.
The prefetch helps it pull it from memory over time. It could be pulling from this, but it's actually caching. It's gonna read everything on disk and cache it up into memory, and that's what makes it faster the next times that it goes through.
Okay.
That makes sense.
In one of my notebooks, we're going to see on Friday, I thought my notebook was just frozen because it took a very long time to start the first epoch.
So I don't know if you remember when we ran with VG16 in the tutorial, we got a val loss that was like 0.308 something. Here, we're not going to achieve that. We're going to get down to, I think the lowest is actually this last training epoch, which is 0.36. And the accuracy on the VG16 was 0.8, was 87 something percent, and here it's 85. So if we plot this, we'll see one big difference now is that our curves are very close together. There's not a lot of problem with generalizing between our training set and our validation set. So they've kind of stated here to make you think about it. They've said that the training loss and validation loss are fairly close, and that's evidence that the model isn't just memorizing the training data, but learning general properties of the two classes. Yeah, I'll agree it's generalizing some, but they also state that it's likely it is underfitting some. Remember, we were overfitting with VG6 and could use some benefit from the extra capacity. So one thing I noticed when I read that was that our validation loss and our training loss, while they are starting to diverge a little bit, they're still going down.
Mm-hmm.
So we really can't say that we're overfitting or underfitting, because we really, it is underfit in the sense that we haven't run enough epochs, but it's not because of the capacity of the model, is my point.
Mm-hmm.
So I wanted to test that. So I actually put in some more code here to start at, 30, which is just for writing it out, but to run it for another 100 epochs and see what happens, right? So I'm just gonna, I haven't recompiled the model or done anything, so I'm just taking the weights I have and continuing to train from here. And I thought this was interesting. I'll show I have a plot down here. So from 30 onward, it did actually get better on the validation, but we definitely started to, really diverge in our training and overfit the training. But when I looked at this result, it got better. I think VGG16 was at 0.30 something, so we didn't reach that level. And our accuracy, our accuracy didn't, right around here, we got pretty close to the 0.87, but not quite there. So we definitely aren't as good as the VGG16 out of the box. Probably we could do a lot of things to increase the capacity of our model, such as working on a little more dense layers than we have there. We've got a very small head on this for doing natural classification.
Could you say again what's going on with the initial epoch equals 30 there?
It's just for printout. It's just because they had done 30 the first time. If I didn't set that, my first one would have said epoch 1 of 100.
So you were starting with the original training result after 30?
Yes. Well, the model. Yeah. So I'm using the model's weights after it's trained the first time, right?
Mm-hmm.
And I'm not resetting everything. I'm just starting training again. I'm just doing the fit and continuing on. And so just to have it label them as this is number 31 really of my epochs, I just put that. You can put that. It's just a convenience. It doesn't go back and start it whatever you put it at. It's just how it labels.
Right. That makes sense. Thank you.
So it's just for a printout to make it pretty.
It's funny how they ask you to stop how they have you stop after 30, because things are actually looking pretty good at about 30. They're they're kind of tracking each other pretty good. And then after that, it looks like,
Yeah, things
Yeah.
get
yeah, it looks like it's like seriously overfitting after you run 100.
it does definitely start. Yeah.
Yeah.
So the other thing too, whoops, sorry, it's hard to get. The other thing too is maybe the scale here is going to be different too, right? So before it was up at like, I think it started up at like 70 or 60 or something, pretty high, right?
Mhm.
So this is a smaller scale, so it's going to look bigger. The gap's going to look bigger than it was.
Oh yeah.
Right. So there, so that exaggerates. It's not. I could do something with the plotting to make it a little more apples to apples. But what I was mainly looking for is the fact that it hadn't reached the best result yet, right? So I wanted to see if I was comparing VGG 16 to this Inception model and just saying, well, what is it really that much different? So
One thing that's a little bit noteworthy about these figures, I think, compared to many times when we've run neural networks and trained beyond the point where they overfit, is that there's very little noise. It looks very smooth. The validation loss and training loss seem to very, very smoothly. Is there a reason for that?
I think that part of it is the nature of transfer learning. We're only training a really small classification head, right? And I think that's probably a lot of it, actually. Maybe you have another idea for it, but that would be, and my initial thought is that it was a little messier with VGG 16 on their tutorial. You can see there's definitely some instability here. So it's a good point is, it's maybe a difference between the two pre-trained models.
I also think the data set itself is well behaving, meaning you don't have like weird pictures, I think, because later on we're going to introduce like draw path layers. You're going to see that non-smooth effect.
Possible.
I have a question.
Yes.
Does it talk about the different pre-trained models you could choose from, and like if you're starting a new like image classification task from scratch, which one you use? Do you experiment with a couple?
They did not discuss that, and that's a great point. There's lots of choices.
Mm-hmm.
A couple things. I mean, if I was to give somebody some guidance, a lot of the pre-trained models have been trained for specific image sizes, so that can make a difference in which one you choose.
Yeah.
And then you want to think about what were they trained on. ImageNet is a very popular set of data for people to train on. But if you're doing something like face recognition, there's something out there called VGG face data set. That's probably a better choice to choose a model that's been pre-trained on that. You'll get better results on faces. So that's another thing to keep in mind when you choose a pre-trained model. And some models use a lot of resources. They're just big, and you may not, if you're going to deploy out to a phone, consider your final destination. We've used one called MobileNet, which is really popular for like more edge device type applications. Does that make sense?
Yeah, that's helpful. Thank you.
Okay.
Wait, I have a follow-up. Do you happen to know, this is not in the course, I'm sure, do you happen to know if there's like some central way to like look up different like different pre-trained models and their like various attributes? Like you listed a number that you might consider. Do you know if that's all in one place somewhere? Maybe the Hugging Face library? No, that's NLP, sorry.
Yeah, the equivalent kind of is TensorFlow has their hub, which has a lot of them. The other one is this thing called TensorFlow. They have them on GitHub. They have a model garden, I think it's called, where they have a lot of them there, and it's got information about. I don't know if they have like a nice table. They may actually have a nice table where it lists like the number of parameters that it's and what it was trained on and pre-trained on and things like that.
Thank you.
That would be great. And if I haven't looked at the model garden in a while, so I'm not sure. maybe someone else knows.
I think papers with code have something similar because it shows like which models were winning which competitions by then. So maybe when you look like bro state of the art section, I guess they show some of the pre-trained models that work well for specific problems. It might be helpful.
Yeah, there's a lot of benchmarks out there, sites for that. I don't know if they always show like all the parameters and you know, specs of each model. They usually show like what their performance was, but not necessarily breaking down everything about the model. But yeah, that's definitely a good place to start. Yeah, I agree. All right. So let's try to get more into what's going on underneath the hood, and we're going to look at you've heard me talk about convolutions, and let's try to think about what that is. So convolutions are generally, when we're talking about computer vision, it's a layer. It's actually a unit in a layer in a model. So we'll talk about the basics parts of a CNN, which is the convolution layer, the activation. In this case, we'll go over the rectified linear units, and a pooling layer. In this case, we'll discuss the maximum pooling layer. So the first point is that the convolutions are part of that base part of the model that I showed where we do feature extraction. And normally you have many convolutions in different layers that the data passes through to pull out multiple features. The feature extraction that is involved is, you can think of a convolution as a filter. If you've ever worked with like optical filters, applied them to images, that's essentially what a convolution does. So it's going to be like a filter for an image to pull out a feature, what's called a feature map or an activation map. And then we're going to detect that feature with a ReLU activation, and I'll show how that works. And then we're going to condense the image some to enhance the feature, so to make those features stand out more. And that's what we're going to do with max pooling. So here's an example of what happens. We've got our input image of a car. We're going to run a filter, which, if you look at it, it's kind of eliminated color, but it's also highlighted lines and objects against background, right? So we're highlighting some of these things to make them, to detect them. They don't go away, they're still there. When we apply the ReLU, it really does eliminate the background and pull in those now features that we've created. And when we do the max pooling, the condensing, we're just going to exaggerate those or enhance those features a little further to make it easier to see them. So that's essentially what we're going to do in a layer in the CNN. So the first thing we're going to go through is the convolution step. This is often done in Keras with a Con2D layer, where we define something called filters and kernel size, and we'll go through that. The filters, we just talked about what those are, and this is how many are in that layer. So in theory, this layer could produce 64 for each image. It could produce 64 of those outputs of feature maps.
Question.
So go ahead. Yes.
The 64 filters, are they predefined, or is it learning those filters from the image input set?
Okay, so I'll take care of that in the next little section here. Good question. So this is an example of a 3x3 filter, which is what they call a kernel size. Another way of referring to this is a kernel instead of a filter, but this is a 3x3 one. So this is one of those 64 that are here in the layer. Each 3x3 filter is going to have a set of 9 numbers in there, which are weights. These are they're just showing -1 and 2, for example, but these are the weights that are learnable by the model. So the model, as it trains, learns which values for these numbers provide the best filters that produce the best features that are useful for whatever our task is, classification in this case, right? So these weights are trainable, all of them are trainable. Does that answer your question, Chris? I think it was Chris, right?
Well, more or less, yeah.
Okay, and we'll show more examples of that. But if you can imagine, we're doing this in this particular layer, we're doing this for 64 different one of these, right? So how do these work in regard to the image? So here's an output showing kind of what happens. This 3x3 filter, or kernel, as they like to call it, is being applied to the image input and producing a single output. I mean, this is a good example. You would then move it over like one row and apply it again, and it would produce an image here, or sorry, a new pixel value for here, a new feature map value for here, right? A new number. So how does it do that? I thought I would show a different example. I like this a little better. So this, can you guys see my cursor? I assume you can, right?
Yes.
Okay. So if this big block is my image, and here's my kernel, my convolution, and I'm applying it to this section of that image, the first block on the, each one of these numbers is multiplied by the space over here that aligns with it to produce a value, and then the values of all of these numbers times each other is summed up. And here's a great example of that being done. You know, the 4 goes to the 0, that gives you 4 times 0. There's a bunch of zeros here that produce all these, even the ones multiplied by 1. And then in this last one, you got a -4, and that's going to go against 2 here. And then when you add up these values, you get a -8, and that goes now in the center of our new feature map that we're producing. So this is going to be the output. And then we're going to slide this. George is going to go through some of the different parameters you can set for how you slide this kernel over the image. But we're going to move it to the next block over by 1, for example, and that would then be applied and produce a new number here and a new number here. And then we also move down and we produce new numbers. So we get a whole bunch of new numbers that represent our feature map that comes out of this. So that's how a convolution produces a feature map. So that's kind of what they're showing there. I mentioned the kernel size. It was showing examples of a 3x3. These can be different sizes. 5x5 and 3x3 are the very are usually the most commonly ones used. They don't have to be, but it's the most common. So we mentioned these feature maps here. They're showing if these different feature maps were are these different type of kernels that maybe it learned these weights were appropriate. This one where you have the -1, the -1, the 1 and 1 is actually going to look for horizontal lines. So it's going to emphasize horizontal lines. This one is going to do something. Let's see. I always have to look through them. I think this is
me.
What's that?
It looks similar to me, like another horizontal filter.
Yeah, it's sort of a highlight. It's called a. I forgot what it's called. Something with a B. They show it further on down.
Sobel operator.
There you go. Yeah, it's called a Sobel filter.
Operator.
And I don't remember exactly. I think this might be some kind of diagonal line finder. I can't remember exactly. You know, maybe the grill here is getting more attention because of this. Some of these lines coming diagonal here are getting emphasized. So just some examples there. So now we've got that output, that feature map, and we're going to detect with our ReLU function. So the ReLU is based on the rectifier function where anything below 0, applied to any number below 0 gives you a value of 0. So you can never get a negative number, you always get 0. If you input, x equals 0.5, you're going to get 0.5 back. If you input x equals 1, so it's linear on the positive side. So if we apply this to our output, it effectively will take all those kind of, well, let me show you the other, on this other page, any negative numbers that are coming out here, the ReLU is going to make those zeros. And any other numbers, it's going to leave them, any other positive numbers, it'll leave them as it is. So I'll show you an effect of that later on. They gave a good example. Sorry. Missing off the screen. Back to here. All right, so that's put in here as an activation equals ReLU. Here's an example of the ReLU being applied to those prior lines. I said this was like a horizontal line kernel. And so it got all the other noise out and it kept those horizontal lines. Here's the next one. And then this was kind of what I thought maybe was a kind of diagonal line emphasizer. But you can see now that it's actually emphasizing detecting those features that are in the feature map. So for this example of a car, we're going to show applying a raw kernel to this image. So a raw filter, right? And this one, we're going to basically emphasize things that are, I believe, what's it going to do? I can't remember. This is just any edge detection, right? So it's going to look for any edges in the image. Which, if I looked at this image, I would think probably, the grill, the lights, the bars up here, the mirrors, maybe so the outside of the car, things like that. So we're going to use a raw convolution layer here. This is not Keras. This is just straight out of TensorFlow, but it allows us just to input an image to it. We can apply that filter that we showed before that's going to detect edges. And we'll talk about these in a later lesson. And we're going to just display what it puts out. And here you can see it basically got all of the edges that were visible in the image. So that's that. And then we're going to apply the ReLU to it, which will make those even more obvious by getting rid of anything else in the image. And we're going to now look for the exercise about this. So any questions on how the theory there?
Yeah, something kind of interesting there.
Yeah.
When I went through the Kaggle course, I noticed that too, that with the one from TensorFlow, you can actually give it a fixed kernel to work with, but at Keras, it looks like you can specify a number of them and have it kind of pick the ones that it uses. How does it do that? Do you know?
Well,
if you tell it 64, how does it know which one to pick? Does it just go through all of the images and then try to fit a set of 64 that it thinks might be the best and then adjust the weights accordingly?
So you're going to give it 64 that are randomly initialized weights on them, right?
Oh, okay.
Those kernels, and it's going to do training, and it might decide that only maybe 16 of those kernels provide anything that's valuable to actually do a classification, depending on how your images are simple or complex they are. So some of those the weights might get zeroed out, and they're not really going to be used, right? So 64 might be overkill, and your model might do better with a smaller number, or maybe 64 is not enough.
Huh.
But does that answer what you're talking about?
Yeah, kind of does. I was just curious about that. That's really cool, by the way.
Yeah, the advantage here is we're putting in a kernel where we've already defined the type of filtering we want to do, right? And we can apply any image to that just through putting it in here. And it's not learning any of the weights. It's just saying, well, if we give it those weights, that kernel type, what does it do to the image?
Oh, okay.
So this might be a valuable when you're doing with Keras and you're doing actual training on a lot of images. Maybe this is a kernel, this edge detector that, and it probably is, there'll probably be an edge detector that it learns is very valuable to classifying objects as cars or trucks.
Yeah, somebody up in the chat had a question too. I think it was Kuldeep asking a question: does the sum of all the values in the filter all have to be 0? Because so far it looks like they are.
Do the sum of all the values in the
If you go back,
no, absolutely not. No, in fact, I believe if you look at these, right, as an example, this is a 2x2 filter, and,
yeah,
and these could be zeros. I mean, They've done this because these
All
are
the ones they have are add up to 0. It's kind of an artifact, isn't it?
Yeah, it doesn't have to be this way.
No,
The one at the
no,
end.
I'm sending something in the chat.
Okay.
When the numbers add up to 0, then you typically get a very dark result, which has a lot of dark pixels, and this is edge detectors, filters like that.
Yeah.
If your numbers add up to 1,
Brighter.
then you get what's usually a sharpening filter.
Like-
You end up with the same color balance that you had in your original image, but typically the edges are a little sharper.
One in the end is adding up to 1, right?
This one.
Yeah.
Yeah, because you've got this one in the middle, right?
Mhm.
So.
Can I ask a question
Sorry,
as well?
So this.
Yeah, go ahead. Sorry, Vladimir.
So
Vladimir,
I just
you
want
can
to say, basically, this is, yeah, sorry, yeah. So there is, this is coming actually from image processing. What you see there, +1 and -1, for example, the first filter, which is edge detector, is actually presenting a first order difference approximation. So when you try to do edge detection, you try to find differences, which is actually making the derivative of the image on the vertical. Now for the SOPL, the second is more complex because the SOPL operator is actually a combination of two filters. One is integrating and the other is differentiating. So when you have 1-1, that's integrating filter, which is kind of creates the blurring effect because it filters the high frequencies and keeps only the low frequencies. Whereas when you have -1-1, this is differentiating filter, which keeps the high frequencies and removes the low frequencies. So it preserves the edges, whereas removes the texture. So I sent in the link something, it's like there are a couple of images there. So there's kernels and then one image and then what happens to them. So things like edge detection, sharpening, blurring. There's also unsharpening. So just look at them after you finish. So it's not necessary that they sum to 1. When you to 0, when you sum to 0, you don't have a DC offset. But when you have something that is different from 0, you have DC offset. But again, you have to understand how the filters behind that work on the image in order to, let's say, imagine how the result in the output of the processing will look like. So it's not really kind of straightforward. You have to think about it.
And I like to keep in mind that these are purely just for examples of how a convolution could be applied to an image. But in our neural network, we're learning all these values and learning all these weights and what convolutions and kernels are the most useful for doing classification. So
it really puts it into perspective when you think about how much research has gone into designing filters for image processing over the years, and now how neural networks are just able to find these things that took people years to work out on their own.
Right. Okay.
Something else that I just went. Okay, sorry.
You had a question too, Vladimir, didn't you?
Sahil.
No, I just wanted to add. So.
You just said that.
So there was a question. So there was a question about this, why we have 64 filters, what are they doing and things like this. So I think this can become clear later on when you look at the whole, let's say you have several kernels, several convolutional layers. So the higher you go into the deeper you go into the network, the purpose of these filters that get learned, these kernels that get learned, is to look at a larger part of the image and to understand the image as objects, whereas the first layers are to do this kind of edge detection or blurring and things like this. So the different 64 layers in this case, they have probably the same type of behavior, but they have different coefficients, which later on, so on the next convolutional layer, help create something that resembles an object. There is a kind of article that is paper that can be helpful if you're interested how actually, so in order to understand what happens on the first layers, you have to kind of look forward in the next layers, and then see how the network processes this and tries to understand what actually is going on in the input image, based on the different steps basically that you do on each convolutional layer. Okay, I'll put the article, the paper there in the chat right now. So it's not the answer is not straightforward. Why 64, not let's say 32? That's a different question. But the number of kernels that get learned, let's say on the first layer, helps the network understand the image on the later layers. Okay, this maybe not very clear, but
that's good. I think I've seen some interesting examples where, like if you look at the actual feature maps of an actual train network, you can you can actually see it, kind of visually see it. Like the first layer usually picks out like things like edges and colors and very low level features of an image, and then as you get further, further down to the later layers, you start to actually see like actual features. Like if it's, for example, if it's the images are of like faces, for example, you'll actually see like little segments of a face, a nose or an ear or something. You'll actually see that visually in some of the feature maps. So you can kind of see like how sophisticated the features have gotten as you get further into the network.
That's
also, one other thing before we get off this, for this exercise, just sort of a reminder that we're using pre-trained base. So all the coefficients, all of the convolutions are done in the base, and all of the coefficients have been pre-trained. So we're not, in this exercise at least, we're not learning those coefficients. They're already set based on the base model that's used. But if you were training something from scratch, then yeah, you'd be training all of the coefficients for the, I'm calling them coefficients, but I should say weights for the kernels, the convolutional kernels as well. So, yeah.
So let's move on to the exercise where they show some of these. Again, we're going to look at our image with our car, and here's some of those filters they were showing. These, we're going to define our own one here, which again, we've seen this before. You could put, I think they allow you to put anyone in here. I just chose this edge detector and applied it. And then once you've got that, we're going to go ahead and show what it detected. Again, it's detecting these edges. We need to apply the ReLU to kind of make everything that's negative go out. So we just have the features by themselves. And this is very much what we saw in the tutorial. The one difference here is they're going to show an image, which you see is this second column is ones. We've got a few ones in here, and everything else is zeros. We're going to apply this filter, which, if we think about what it's going to emphasize, does anybody know what this is? This is, we saw a horizontal edge detector. This is the equivalent vertical edge detector, right? So if you think about what it might see in this image, we've got background or nothing really here in the pixels, and we've got some pixels along this line, this vertical line, and we've got a vertical line on this half of this part of a row. So when we apply this, we will probably see that it's going to pick that out. So here is going to be a very similar thing, right, where it went through, we applied it to that guy up there, and this is what we got back. And when we do our ReLU against this, everything that's below zero is going to be made a zero, and everything that's above zero is going to be a linear function. It's going to be the same value in as output. So we now have a vertical line that it detected. If that makes sense. So any questions on that? It's pretty much just what we did in the tutorial, just to highlight.
Yeah. Just something to clarify, because I think it's confusing people. So the color that you see here in the exercises and the tutorial, I think that's just a color that Kaggle chose to highlight the contrast, right? I think this purple looking color.
Yeah.
Because your input was gray, right? So
it could, yeah.
And another question is, your image could be, so it has 3 channels. You have a red, a green, and a blue channel. In this case, we just have a very simple one dimension on one channel, the gray one. But in reality, you might have multiple channels. And then in that case, your filter gets applied separately into different channels.
Separately in each channel, that's right. Yeah.
I have a question.
Yes.
So in most of the examples, when they try to show the effect of kernels, they try to pick the values in the kernels integer numbers. But I'm assuming not necessarily when you learn the values of those kernel points, they're not supposed to be integers, right?
They're allowed to be any values. The weights are gonna, be. They can.
Because
like any other neural network weights, they don't have to be. They don't have to be integers at all.
Yeah. What I was thinking, because most of them they use like -2, -1, 0, 1, 2. If you have 2 by 2, if you have 5 choice, it's going to be kind of 5 to 4. And then if you pick number of kernel size bigger than that number, maybe you will be getting same kernels over and over. So I was thinking then integers wouldn't work well. So I think that makes sense. It should not be integer necessarily.
I'd be surprised if I saw anything in integer in any deep learning model.
Yeah, sure.
All these vectors,
for weight, definitely not. Yeah. All right, so let's go to the next step that's usually applied after our convolutional layer. We usually apply pooling layer, and here we're going to look at maximum pooling. So they have some good examples. Here's how it's done in Keras. Here's a 2 by 2 pool size. So what pooling does is the following. It emphasizes these features that we've detected, right? So it makes them bolder, bigger. How does it do that? Well, here's an example. If we think about, this is a section of 2 by 2 of the image that we're looking, or the feature map that comes out of the convolution that we're looking at. The maximum value there is just black, right? So there's no real color. So that's what it now converts every value in that 2 by 2 block to the maximum value. Here we've got kind of a combination. Turns out these guys, I guess, produce pretty much a max value here. This is the brightest max value, so we give the whole block that color. Here it's the orange. Here it's going to be this yellow. Here it's purple. And again, we're back to black. If you apply it over the whole image, you see now that we still have a similar type of feature shape, but it's emphasized. It's gotten much stronger and much more prevalent against the background. So that's what max pooling is going to provide for you. So they show that again. We're going to get to this stage where we've got our detected models with with our features, and we're going to try to use this pooling feature where we're going to do it on a 2 by 2 window. We're going to do max pooling, as we said, and we're going to apply it to our image, the same image we used. And here we can see the difference of how that affects it, right? So this is our example of doing it just on a single image. I will say that there is no weights associated with pooling. The only thing we're doing is setting how large are these squares. So in this case, we're doing 2 by 2. You could do 3 by 3, but 2 by 2 is pretty standard. And so that's the normal thing that pooling does. There's no learning on the pooling. We're just doing a application to emphasize the features we've already found. There's a couple of neat or not so neat aspects of max pooling. One is that if I started with an image that's 32 by 32, and then I start doing the pooling, I get down to now an image that's reduced. Every time I do this, I'm reducing the number of blocks to, half in this direction, half in the opposite direction. But then I'm emphasizing those blocks. If I keep applying pooling, the same pooling over and over, these two individual features will now merge into a single one. So if there was something significant about that positional information, we've lost it. So that happens. That's one thing that we lose is positional. We can lose some of that positional information. But an advantage can be shown here, where this type of ability to, this image and this image, now you can move them around. They look very much the same. It's called, they're invariants to positional difference. So if, I guess the way to say it is, if you had this object here and this object here, you still have that positional relationship. Sorry, I'm just not saying the right way here, but the best way to say it is that you sort of get a way of doing some augmentation information there, in the sense that your rotational translational augmentation doesn't matter, right? So translation would mean, you're flipping these over, you don't see any difference, right? So
to me, at the end of the day, you have basically divided the input image into 4 quadrants.
Yeah.
And you're able to distinguish things that are in different quadrants. Like in the second example, there's 2 dots. As long as they're in separate quadrants, 1, 2, 3, 4. In the end of the day, you're going to end up with that image. But in the first place, both of them are in the same quadrant, and you can move them around as much as you want in the first quadrant, but always you will end up with this one
right.
representation that you have in the end. There's no way to.
That's where the translational invariance comes in, is that no matter where it is in that first quadrant, as long as it's in there somewhere in the max pool layer, it'll show up.
Yeah. So small distances are not, you don't see a huge difference if you move things by a small difference in the very end layer. But in this case, we have a large difference, and that makes a big difference.
So the idea is that we didn't lose that because they started with far distance. We didn't lose that information about positional, right? Because we still know that they're across from each other, right? Mm-hmm. Whereas here we're going to lose some of that.
Yeah, effectively, what the max pooling layers do also is they reduce the resolution a lot. So that's partly responsible for the property of that transitional invariance.
Mm-hmm.
Yeah. So, I mean, if you think about it, what's going on here is that it's effectively being max pooled 16 by 16 from the left image to the far right image all at once.
All at once, that's right, yeah.
So the example actually seems a little bit contrived to me, because I don't recall ever seeing max pooling done in succession like this. Aren't they almost always split by convolutions?
They are, yeah. Yep.
No, this is not a network, this is just an example.
Yeah, and if you want to take the example out to the ridiculous extreme, if you had 4 sets of those little shapes on the left and on the top row, it would still show up as the same image on the right-hand side, because it's max pooling. So if they're both there at the same intensity, you effectively fold it to 2 or 3 or 4, or however many of them there are, into one.
Right.
Now that we picked apart their example.
Oh, it's always fun. I'm sure it's hard to make these courses.
I think the max pooling, like it's the fact that it makes the image smaller each step of the way is a really important property, because generally for this kind of classification network, each layer, as you go down the layers, you get like, the images get smaller and smaller, and then, but you get more and more, generally you get more and more filters each time. And then by the time you get to the end, you end up, going into the dense layer with almost a very, very small image at that point.
That's right. Especially important when you flatten it out. Yeah.
Yeah.
Yep. Exactly. It's very.
Yeah. Yeah. The max pooling layer too looks like it'd be useful for doing multi-scale detection as well, because in a lot of the examples that in this course and other ones, the images are all at about the same resolution, and the information in them is at about the same spatial scale. If you're going to do something like a wavelet or a Fourier transfer on them, the distributions would look about the same. But it's often the case that images have kind of an inherent structure going from the coarse scale down to fine scale that can greatly aid the accuracy of classification. So I think that's one of the, I want to call it dense net, but I'm not absolutely sure, where you have actual bypasses from, instead of going in a strict hierarchy, you actually have connections that actually go from lower layers up to max pooling to other ones.
Many networks use that. Many. So dense net is one of them, but there's many others.
So I just want to add something. So just one point. So this max, it's a nonlinear operation. You can also have average, which is kind of linear. So you don't take the prominent feature from the feature map that you select from, let's say, your block, but you can have also average. Now, I don't know why max is so popular. I think maybe some performance reason, but the reason, when you let's look at it as like a wavelet transform or Fourier transform, in which you have this multi-scale. This works as well. This works as long as you have some kind of linear transformation. This max pooling, you have non-linear. You just select one that is the largest of a block. So I don't know how actually can be translated to the point of Chris.
Yeah, so I was going to point out, the other option here, as you mentioned, is instead of just taking within this size, you can take, instead of just taking the maximum value pixel, you can take the average of all the pixels in there and replace, the one pixel here with that average. And so that's what you were referring to. I suspect, this is just, off the top of my head here, but I suspect that max pooling, it is definitely favored. And one of the reasons might be that it tends to, if you have a very, an image, here's an example, right? So maybe this little feature right there, or part of the image, is really important, but when you do average, you wouldn't get this purple anymore, right? You get something much less emphasized. And so max pooling keeps that as a very important thing. And maybe in some cases for some image classifications that can be important. There may be other reasons, but that's
yeah. If you imagine your convolution output as, if your convolution filters as detectors, it might be detecting some particular feature within your image space. Maybe it's trying to detect an edge in the lower layers. Maybe it's trying to detect a face in the upper layers. Right. Then what you want to do, maybe for your final output, you just want to know, like, is there a face in my image? And so then if you take the maximum of those pixels, it's basically, did any of them detect it? So I think that's a part of the theoretical reason for why max is preferred.
Yeah. All right, I want to get to the exercises so that I can turn it over to George to finish his part. So again, this exercise is on the max pooling. It's very much what we saw before. We're going to look at a car. We have what's called an embossing kernel. And we're going to apply it. So here is what came out of that. And we're going to use pooling to change this into a smaller size, to condense it down and emphasize those features. So, what happened? Oh yeah, so here's the application of it. Just so that image is 2x2, we're using max pooling, and we're going to run it and show it. So here's the output. It doesn't really show up, but this would be a smaller sized. They just showed it side by side so you can see what's happening. But you can see, you know, how it's really emphasizing these detected features now are being pointed out. They have some ways you can use this particular original shape here and apply successive max pooling, kind of like we saw before, and see how it turns into like this when you get to 4x4. So a very small representation of that. So if you want to go back to an Atari version of your images, just go and apply this method.
I was about to say, if you want to have higher end graphics, you should do the opposite of max pooling.
That's right. So I thought there's some interesting things here. So so here's something called, instead of max pooling, we're going to do global average pooling. So if this is our feature maps that we came out with, different ones, right? So we had in those units, maybe in our ConvNet, we had 1, 2, 3, 4, 5, 6, 7, so 8, let's say. So we got 8 feature maps out. And if we took those and we took each one and we did average pooling, global average pooling over the whole feature. And in this case, you can see there's kind of a balance between the lighter colors and dark, and you come out with this kind of median color. Here you got another nice balance, pretty balanced. Maybe this one down here is a little lighter. You see it a lot more of the light yellow color, so we get an average that's higher value. So that's what is produced when you do a global average. And the way they use that often is to replace the dense, the dense layer where you do the flattening and all that. I don't know, I think, yeah, so here they're showing, right, instead of, normally we'd do our pre-trained base, which would produce our feature maps, then we do a flatten and then some dense layers to do it, right? So here they're showing how that happens on our model. And here they're going to use it for one example. They've trained on our model, and then they're going to show you an example. So here they took the car, and we've got out of that, I think, do you remember what this was? VGG, yeah, VG16. So it's going to give us 512 feature maps that come out of it. So that's these values, which are globally pooled. So each one of these represents a global average of those feature maps. So I thought, well, that's kind of interesting, right? What would happen if I actually did it? So I went ahead and went back to that same thing we did with before with the dense layers, where we flattened it and we applied our dense layers and did our prediction. I did the same thing with that same data set, prepared it the same way, and I did this model. I'm going to use that pre-trained VGT16. I'm going to do global average pooling on the feature maps that come out of there, and I'm going to do my prediction, right? Same optimization, same training. I did 50. And here's the actual result. I don't know if you remember, we got before we got down to for the val loss, we got down to 0.308. Now we're much lower. And our accuracy before was 87 something percent, and we're 97%. There's some instability when it first starts, but once it gets up there, it's pretty good. So I was really surprised to see that replacing that dense net with a global averaging did so well. I don't know. So anyway,
an intuition or just a dimensionality reduction from 8x8 to 1?
No, I think it's the fact that dense net was so small. The head that they had put on top of it was only 6 units for the first dense layer, right? The only dense layer in there. Whereas, so that's my guess, is that there's just not much capacity to learn. When you get the feature maps out of the pre-trained layer, they didn't give the head much capacity to actually learn from those feature maps. And maybe this does a better job of, overall. I don't know. anybody else has. I'd never tried this before, and I was surprised to get such a good result. It actually fits the training set exactly. It overfits, you know.
Yeah. I use it a lot on the exercise we're going to see on Friday, so it performs well.
Okay. So if there's not any more questions, I'll turn this over to George.
Cool. Thank you. Thank you, David.
Sure.
That was super interesting. Let me share my screen. Can you see my screen?
Yes.
I'll literally take it over at the moment you left it. I just explored some more images here. I find that interesting, the combination of input image and feature maps. And if you remember back in the old days when we did the MNIST data set, when we were looking at fashion items like shoe or handbags or clothes, we're trying to classify them by their corresponding categories. So we were looking at a feature map. So here, just some examples of the two different categories. Truck, this is the feature map for that. Truck, feature map for that. And the goal is for the network to figure out, okay, what is common between these two feature maps that I can classify them as trucks. So something is here, high intensity maybe. Car, truck, but then again, high intensity is here. So it's not easy as for us humans to detect what distinguishes, let's say, this feature map from this feature map. But to a complex neural network, you can do that. Cool. Just a summary of where we are. So we covered convolutional classifier, the ReLU, maximum pooling, and we're going to talk a little bit about sliding windows, two more parameters, the stride and the padding. And then after that, we're going to train our own networks from scratch and some more features like data augmentation that will help us with our accuracy. Cool. So we saw the convolution operation, we saw the maximum pooling, we saw the detection part with ReLU. The last thing we need to talk about is when we look at the image, how often or how much do we move horizontally or vertically? That's called the stride parameter. Let's look at an example here. So far, I think what we've seen so far is stride of 1. This is the parameter in Keras. So it's a parameter of the convolutional 2D convolutional layer. So we defined our filters, our kernel size. In this case, stride 1, meaning in both dimensions, both horizontally and vertically, we're going to move our filter by 1 pixel at a time. If we wanted to move it by 2 pixels at a time, as is shown in this graph here, we're looking at this portion of the image. Then we're not shifting to the right by 1 pixel, we're actually shifting to the right by 2 pixels. That's the first argument. And then when we go down, we actually are going down 2 rows at a time instead of 1 row at a time. So that's a 2 by 2 side. So let's see some implications of different stride sizes and how they impact our image. Before we do that, one more thing. If you noticed, especially if you do a stride of 1 by 1, pixels that are towards the center or on the inner part of the image will be scanned by a kernel multiple times, simply because they overlap. But pixels that are on the border side of the image, they will probably be scanned only once. So if your image has some important features on the outer border, then maybe we're putting more weight on the inner part of the image versus the border. So for most images, that might be okay. Maybe we have something in the middle of the picture and a background. So maybe we're just interested in detecting features from the middle of it. But for other images or from other data sets where we're actually interested in the entire data set, especially as we go deeper and deeper in layers, there's information on the border of the image. We want to preserve that information. So to do that, we use something called padding. And there are 2 types of padding that we can do in a convolutional layer. One is what is called the same padding, where we basically want to make sure that we treat the pixels on the outer border the same as we treat the ones on the inner border. So we actually pad, as you can see here, an actual row and column, an extra one at the top, one at the bottom, one on the left, one on the right, with the zeros. There's no information there, just 0. But what that allows us is, as you can see here with a stride of 1, to actually treat the perimeter pixels in a similar way as we treat the inner ones. If we do a valid padding, then we're not adding this extra buffer, as you can see on the image. We're strictly staying inbound of the image. And what that means is that as we do this operation, our effective size of the image will be reduced by 2 pixels, both on the horizontal and on the vertical side as well. So if we start by 8 by 8, we're going to go to a 6 by 6, to a 4 by 4, to a 2 by 2. So just looking at some effects of padding and sliding windows, we're going to use this filter here that's detecting horizontal lines. We'll use a convolutional stride of 1. The pulling side, the stride is 2 here in this case. So this is the input. This is after the filter, after the convolutional filter. This is after the max pooling, and this is so this is after the ReLU, sorry, and this is after the max pooling, the condensed part. So let's look at another one where we skip. So this was, let's see, this was 1, 2, 2. So our stride now is 2. So we're going to skip, when we read the image, we're going to skip parts of it. And as you can see, it's getting blurrier and blurrier. So our convolution part, it still has some features, not as much as it did before. It's not as fine-grained or as high resolution as it was before. That's because we're skipping parts of the input as we traverse it. And the detection part is also much more sparse. And the condensed one, still the overall circle shape is there, but you can see it's more sparse than the first one. I think the exercise had some more interesting examples, so let's look at that. So we're looking at 3 images here: a circle, the Kaggle K, and another car, and then just some different features. And we're going to see how padding and sliding affects them. So we're looking at the circle as an example. We're going to use the bottom subble feature or kernel. We'll use a padding of valid for the convolution. This is almost exactly the same as the one that we saw in the tutorial. Let's go to the next one, maybe more interesting. So again, we have the input. The stride is 2, so we're not scanning all our pixels sequentially. We're actually skipping one at a time. As you can see here, we kind of lost this vertical line, but that's because our filter is.
George, I think that's the convolution stride, right? That's 3.
Yeah.
Yeah. Okay.
And I'm trying to remember this bottom subble. So that was detecting. So that's detecting, as you can see here, the structure, horizontal lines. So we basically lost this entire vertical line in the K. So here it's almost gone. But the horizontal lines, as you can see here, this part of the K is still present all the way to the end. And let's look at a more.
Yeah, to clarify on that, it's detecting horizontal edges, and in particular, those edges where the top is dark and the bottom is light. That's why you get a bright spot at the top of the K, but not at the bottom.
Mm-hmm. Yeah, so if you want to detect both, maybe you need I don't know if there's such a filter, or maybe you need a combination of filters. If you want to detect both the bottom ones as well.
You could probably best do that with multiple filters.
Yeah. And with a more realistic picture, as you can see in the end, by the condensed phase, it's kind of hard to even realize what we're looking at. But the spatial information is kept there. You have horizontal edges here by the bumper, some here by the front part, by the window. They're still maintained. Cool. Another thing that was briefly mentioned was this concept of receptive field. And basically, the deeper we go to the network, and we started talking about that, the first few layers detect only very simple features like horizontal or vertical lines, or the if the image is like smooth, or if it contains circles and things like that. But as you go deeper and deeper, you actually start to form almost a deeper understanding of what the input image is based off. And that has something to do with the fact that if you look deeper into the network, this pixel, for example, at the third layer is an output of a convolution and filtering done on this 3x3 patch. But then if you look at each of these 3x3 patches, let's look at, for example, the center one again. That one is dependent on the previous layer on another 3x3 patch. Its neighboring as well are also dependent on another 3x3 patch, possibly, or definitely in this case, overlapping with the patches that this one relies on. So if you see this, the short story is that this single pixel has access to information 2 layers down on a much higher spatial height and width, in this case a 5x5 patch. So the deeper the network goes, the more this receptive field is increased. So if you have more and more layers, you know, we see here we go up by 2. So if we keep going in another layer, we'll have access to a 7x7 patch.
Yeah, but the access isn't direct. The receptive field is normally defined as just between the pattern of connectivity between 2 layers, the input and a pixel in the output layer. If you try to cross layers with it, then and then you can kind of run afoul of all kinds of things.
No, there's no direct, right? Because you have nonlinearities. You have the convolutional operation. You also have the ReLU operation. Then you have the pooling operation. So, yeah, indirect access.
Yeah, and visual simulation, actual vision research, the receptive fields are actually hexagonal and not rectangular.
That I'm not sure of. Good to know. Cool. So the question here was, if we had another layer, if we had a third layer, what would be our receptive field value? Would be 7x7. Another one is, we talked a little bit in the chat about kernel size being just a number. In this case, we're going to talk about not being a number, but the kernel size being just a vector, a one-dimensional vector. And we're going to look at some examples for this time series. So this is just a data frame that is hosting this weekly information. I'm not sure what this data represents. Interest, something about interest. I think this is a data science or Google Trends on the word machine learning. So how many people have searched the word Google machine learning using Google from 2015 to 2020? I'm not sure what the units are though. Let's say there are some units. So and you see the beginning in 2015, there was not much interest. And then around 2018, it's kind of reached a high value and then it kind of slowly increasing. And as you can see here, that's probably holidays right before Christmas or before holidays or New Year's. Nobody's Googling that anymore. You see this periodic dips here right before the start of the new year. So we're going to apply 3 different one-dimensional filters or convolutions here in this case. Something called a D-trend. And I think we mentioned this a little bit about the sum of our pixels or the values of a kernel adding up to 1. So as you can see here, they're adding up to 0. Sorry, they add up to 0. So we'll see what this has an effect. An average where we spread out the same value across 5 different positions here, and something called Spencer, and we'll see what that does. So using this D-trend kernel, which is the -1, we'll use a 1D convolution. It's on a 2-dimensional line. We don't have height and width. We just have, let's say, position. And we will apply that to our original data series, which is TS data here, the machine learning one. We're going to do some pre-processing just to convert them to floats and make sure that they are ready to be consumed by our model here. And then at the end of the day, when we look at the result of it, you can see that we don't have an uptrend anymore. We just have this detrended kernel or detrended output of a kernel where the average is about 0, and then you see the interest going up and down. If we apply the average filter, which was a collection of 0.2, 0.2, you see that it has like a smoothing effect. So we don't have those sudden drops. We have them, but not at the same scale as we had them before. We don't have a lot of noise as we did in the original data series. The last one is this Spencer kernel, which looks to me similar to the average one, but maybe it has some other nice properties of smoothing the output. It's kind of hard for me to tell. Maybe this upper part here you see here as well is still kind of noisy, but here it's much smoother as well. Yeah, so the average and Spencers are both smoothers for low frequency components, and the D-trend just removes filters for changes. Cool. So with those new concept in mind, let's see how can we combine them to actually create something on our own. So we're going to look at the different blocks. So we have these new features now. We have a convolution layer, we have a ReLU function, then we have a pooling layer. That is our transformed version. We can combine multiple of these blocks next to each other, so we can successfully apply these operations sequentially. So we're going to look at the same data set again, some pre-processing here just to make sure that we can reproduce the exact same result every time we run this. Some display features. We're going to look at again at the car and truck data set, 128 by 128. We'll look at 64 images at a time. And when we train, we're going to shuffle them so that we don't get the same order again and again, so that somehow by mistake, our model picks up the order of images while it's doing classification. Same more or less pre-processing as David covered, caching, the prefetching. And if we look at our model, we want to build this simple network. So we have our input image. We want to apply a 2D convolutional layer with a kernel size of 32 filters. So our model will actually start with 32 random filters, a 3 by 3 each one of them. And eventually over time, they will be learned, and hopefully they'll detect some simple features here. But as you go deeper and deeper, they'll be able to detect much more complex features. So as you see here, we double the number of filters in the next block, 64, and then we double it again, 128. Then at the end of the day, we flatten this and we pass it through a DNN, to a dense neural network. At the end of the day, we only have two classes. That's why we have units 1 here and a sigmoid activation function. So anything less than 0.5 will be classified as one category. Anything more than 0.5 will be classified as the other category. So we'll import Keras, and from TensorFlow Keras layers, just layers so that it's easier for us to write down this conventions. So under layers.conv2d, we will specify 32 filters, 5 by 5 each. After the convolution operation, we'll apply a ReLU. We'll do padding the same so that we actually pad information around the image. The input image is 128 by 128 by 3. We have color here. After that, we'll apply a max pool layer, and then another block, increasing or doubling the size of filters, max pool, doubling the size of filters, max pool, and then our head or DNN. A summary to see number of parameters. You'll see the conv2d has parameters, max pooling has 0 parameters, flatten has 0 parameters. Our dense, this dense will have the most parameters because it's taking out this flattened version and connecting it to 6 neurons. And from those 6 ones, we're going to connect to only 1. And that's the last one. We'll use Atom, which is a very popular optimizer with some pre-default ones settings. This is a binary classification, so we'll use what is called the binary versions of loss and metrics, in this case, cross entropy and accuracy. We'll fit on our training. We'll validate on our validation set. We'll train for 40 epochs. If you did this in production, you'd add way more configuration settings here, but for now, we're just going to stick with the default ones. Let's look at the graph. I think it's easier to look at. So as you can see, our training loss in blue is continuously decreasing, which that's usually the case, but our validation loss, which is what we're looking at, reaches kind of like a low minimum value around 15 epochs, so 0.5, but then it starts to diverge and act up. Same with the accuracy. For the validation accuracy, that's the main one that we're interested in, is we're about 0.7 something, close to 0.8. But you see the gap between the training and the validation accuracy is increasing, so which is a sign that we're overfitting and our model is not learning features that are transferable from one image to another, but instead it's fine-tuning itself to something specific about an image track or a car, an image or a track image or a car image. Cool. So that was the combination of multiple blocks. Let's look at the last one where we do some, sorry, no, this is the exercise. I'll quickly go over it. Let me see what we define here. Oh, the thing that we define here is a dropout layer, and we'll see the effect of it. But other than that, the similar structure with blocks, conv max pooling, conv max pooling. In this case, in the block 3, we added 2 convolutional layers back to back. And the other new thing is we added a dropout layer between this dense layer and the last dense layer. So what that is telling us that each time we train this network, about 20% of the connections between this layer and the last one will be dropped. Just to make sure that we're not overfitting, we're not tuning, or the model is not picking up features that are specific to the input image. Instead, it's hopefully picking up features that are more generalizable. In Keras, you can do TF Keras, utils, plot model. You can give the model number, show shapes true if you want to look at the shape number, and you can look at this more visual way of the input and the output of each layer and what is the structure. We'll use the same compile method and loss metrics and optimizer. We'll train for a little bit longer, 50 epochs. But let's see now how we are doing. Just a little bit better in terms of validation accuracy, the orange line. We are, I think, touching or maybe crossing a little bit 0.8. And after that, we still see the divergence, maybe not as much as previously, but still we have, I think, an overfitting scenario here. Same with the loss function. Okay. Yeah, so prone to overfitting and need some more regularization. And so we help this a little bit by dropout, but there are other ways to improve on this as well. Another great ways to help us with the overfitting is called data augmentation. Now let's look at that. So with data augmentation is we're going to basically do some minor tweaks on our input data. We're going to augment them in different ways, and here are some examples, so that hopefully our model will be able to detect some features that are common in all these augmented versions, and we'll be able to more easily extract information from the image and realize that this is a car, regardless if it's tilted by 45 degrees or if the contrast is increased or decreased, or the background, or if it's tilted or if it's flipped and so forth. So this is done what is called online. So meaning that you do this kind of random transformations as you fed your images to your model for training. And you do them at, so you present your model with mini batches, right? So in this case, I think it was 64 or 16. So, and you don't do it on all of them, you do it on a subset of them. But in this case, let's say if you wanted to visualize some random data augmentations on this, on various input images, you'll see that some of them have some random part of it missing. Some other ones are playing with the contrast. Some other one is shifted and missing, part of the image is missing. So we're filling it up with zeros. That's the gray part here. Some other ones, maybe it's hard to tell what it's doing. Maybe it's adjusting the width or the height of the input image. Yeah. So that's an interesting data augmentation. And to us humans, that's still a car or a truck. The class didn't change. So the goal is, let me zoom out a little bit. The goal is that hopefully this should tell the network that that's still the same class. Cool. So we started with 5K training and 5K validation images. We're not going to change the number of images. We're going to, out of this 5K, a subset of them we're going to pick to augment each time we train our network. We're going to use this VGG16 pre-trained base. We're going to set the trainable to false. We're not interested in pre-training it. It's already pre-trained on ImageNet. And we'll do some what is called pre-processing. We'll do a random flip of horizontal. So we're going to flip left to right, and a contrast of 0.5, where for some images we're going to change the contrast up to 50%. We'll have our pre-trained base, and then a flatten and DNN as usual. Nothing has changed here. Atom, binary, cross entropy, and accuracy. 30 epochs instead of 50. And let's see our graphs. So first of all, you can see that, first of all, we have validation accuracy much higher than before. We're now at 0.87. Yeah, maybe 872, 873, but it's much smoother than before. We still have a gap, but overall, we are doing a little bit better than before. We still have an overfitting scenario here that we need to maybe add more data augmentation, or maybe a dropout layer, or maybe other ways to combat this divergence of the validation accuracy diverging from the training accuracy. Yeah, that's what it's saying here as well. So yeah, overall, we did benefit a lot from the augmentation. Cool. Let's look at the exercise. I think I have some more examples of augmentation that were more useful. Yeah, so I wanted to look at different augmentation methods just for our own curiosity and how they look like. So look at contrast, flipping, width, adjustment, rotation, translation, and see how they look like. So this is random contrast, 0.5. As you can see, this is the input image. So randomly, we're going to reduce the contrast by 50% in this case. Here, we're not reducing it. Here, we're not doing anything. So the gray ones is when we're actually doing the change. Another thing we can do is the horizontal flip. As you can see, we have the image. That's the horizontal version of it flipped. We're not changing anything. We're just flipping it horizontally. And again, for some images. Another one is the vertical flip. This might not make much sense for this data set, but as you can see, we've flipped everything upside down. And again, not every data augmentation step is applicable for a data set. In this case, for this data set, I wouldn't apply it. A lot of you are working with medical images, so you have to be careful what kind of data augmentation you apply, just to make sure that you still have a valid input image. Random width, this is where we adjust the width of the image. As you can see here, we stretch it out or we condense it randomly. You can do the same for the height. And rotation, we're going to do random rotation from 0 to 20 degrees, as you can see here. This is probably more than 20 degrees. Maybe this is percent, I'm not sure, at 20. But as you can see here, basically we're rotating an image, and hopefully the goal is to train a network that can recognize that this is still a car, regardless if it's pointing, in a weird direction.
So it's normally a factor of 2 pi. So
2 pi.
So 0.0 to 1 of a rotation of 2 pi. But
so 0.2 is okay. So 20% of
2 pi. So anywhere between 0 and
360. So this is up to 1.
It's gonna be up to 72 degrees.
And plus or minus 72 degrees.
Yeah.
If you scroll down a little further, you'll see.
There's negative rotations too.
Yeah, this one here, right? Yep, and this one here too. This one here. Cool. Translation, height factor and width factor. Let's see how that looks like. So we are basically moving the image, or we are looking at a patch of the image on the width and on the height that was specified before. You see here in the end, we don't really see the last part of the car here, or the trunk. Here we adjusted the height significantly. You can see we lost some information here from the background maybe, but we kept the bottom part of the picture in place. And again, this can be a combination of width and height, doesn't have to be just the one. And the question is, which one of them seem reasonable? Maybe the flipping, the horizontal one, or the vertical one for sure. Maybe the translation that we did, the contrast probably are appropriate. And then here's an example of another data set, the Eurosat data set, which has satellite images of Earth classified by geographic feature. So we have a sea lake, permanent crop, industrial, residential, forest, residential. And the question is, what kind of augmentations are valid or applicable here, and which ones are not? Probably rotating, right? Depending on where this satellite is rotating, maybe you wouldn't alter the class. Contrast, I don't know, I'd be a little bit careful with contrast, especially if you want to make sure you don't change the color composition, right? But I don't know, contrast, does anybody think would be a good idea or applicable? Flipping, maybe. Can think of an example where flipping would actually misclassify an image. Yeah. It's interesting to think, right, about what is a valid augmentation. So yeah, flips and rotation will be worth trying. None of this seem likely to confuse the classes. Yep. What if we have a data set of flowers, which we're going to look at on Friday? Horizontal flipping makes perfect sense. Vertical flipping, probably not. You don't want to see a flower coming from the sky. Rotation, that makes perfect sense. Contrast, that's perfectly applicable as well. So let's look at this data set real quick. I think, yeah, this is just a note that some transformation libraries might actually play with the hue, might play with the color composition. In that case, we have to be careful so that we don't go from yellow to gray or from red to blue. And that way, probably we're misclassifying a flower. Cool. So we're going to look at these data augmentation steps: a contrast, flip, horizontal flip, and rotation. And we're going to apply that before we feed it to our block of layers. And the other new thing here is this batch normalization layer, which basically normalizes a little bit the input before it's fed to the next layer. So we've seen in other courses when we apply normalization or batch normalization in the inputs themselves. But if you think about it, each layer in the network has an input from the previous layer. And what we're doing here is we're trying to normalize that in the sense that removing extreme values or keeping track of the mean and standard deviation so that the next layer down the line is not looking at these extreme values. Just a visualization here of the same network that we built. 50 epochs for the binary cross entropy loss and metrics. And we're going to plot our model. So this is again the same, the car and truck. And you can see now with data augmentation, we are doing much better. I want to confirm, is this the car and truck or is this the flowers? Because different notebooks use different data sets.
Flowers.
So that was exercise 5. Let me zoom out a little bit. I think we're still in the car and truck. I didn't see any new. Yep, there we go. There you go. Yeah, car and truck. Oops. So let's look at it again. So you see with data augmentation, we're doing a much better job. And also we're not overfitting as much as we were before. You see the divergence is not as high as it was before. Not only that, but hopefully this high variety of images we're looking at, we're exposing our model to more variety of orientations of car and trucks. You can see that it's helping us also with correctly classifying them. So our validation accuracy is close to 0.9. So as the loss is closely, the training and the validation and the loss are close to each other. Cool. Yeah, so that's more or less what we were talking about. And I'll pause here before I do the plugin for the next session, but let me go to our summary page here. And again, we saw the convolution classifier, the ReLU function, the maximum pooling, the sliding window. We build our own custom convnets. So we explore both transfer learning from additionally from originally pre-trained models as well as built our own. And we look at different augmentation methods. We flipped it, we rotated it, we changed the contrast and so forth. Cool. I'll pause it for just a second in case you have feedback, comments, questions, let me know. Otherwise, I'll talk about the next 2 bonus lessons. Okay, cool. Listen a little bit more. So on Friday, in Eli, we're going to talk about 2 separate competitions. I'll be talking about the pedal pseudo metal one, which is called. We'll be classifying 104 different flowers. I think I've been actively involved in this competition for a while. Right now, I am at 34 out of 348 teams. And Neil is going to talk about this cassava leaf classification data set that we've seen in the past. So it's actually an ongoing competition and there's prize involved. So if you're pretty good at your computer vision models, I would highly encourage you to check it out. The model or the notebook that I'll be talking about, I spent quite some time there. So many of you asked in the beginning, okay, which model should I use? Some said, there's a model zoo. Some said, is DenseNet better than ResNet and this and that? So I actually went over 20 plus different models, and as well as I think 11 tuning methods here. And we'll see here for each one of them. I'm tracking validation accuracy as well as other things. I'm also looking at ensemble models and so many cool things to look at, as well as tracking F1, precision, recall, and so forth. So should be a nice, interesting session. Encourage you to check it out if this is something you like. And I'll share my notebook as well. I'd appreciate if you could vote it. I can use all your votes. I'm very close to getting not only a silver, but also hopefully a gold medal for this. I just need a few more votes. Cool. Yep, with that said, that's on Friday. The then we're going to switch gears from computer vision. We're going to tackle reinforcement learning and some nice, cool new applications. And again, this session is recorded. I'll post it tomorrow on our YouTube channel. You can see here it's getting longer and longer. A few more sessions, and this would be a nice wrap up for this session. Cool. I'll stop sharing at this point. I'll stop the recording and I'll leave the floor open for any comments, feedbacks, or discussion.